Hi everyone. So today we are going to start our new chapter, that is waveguide. So certainly we will study about it, but first let's study about EM wave propagation in space that we have already seen. That was our second chapter. So in open space we have studied about EM wave propagation. Like initially our EM wave was propagating in open space. It could be air, it could be any kind of dielectric, but there was no boundaries there. There was no boundary. It was propagating in open space, right? So for that, what we studied, let's just say if our wave is traveling in positive z direction, if this is the direction of wave propagation, let me change the color of pen. If this is the direction of wave propagation, then certainly our electric field cannot have any component in z direction, right? Our electric field cannot dance in z direction. If this is the wave propagation direction, then electric field can dance either in x or in y. This we have already studied. Same goes for magnetic field as well. The magnetic field can dance either in x or in y. But EZ component will certainly be 0. This we have already studied. And what we used to call this one? This we used to call as transverse electromagnetic wave, because there is no electric field and magnetic field in the direction of propagation. Electric field, magnetic field and the direction of propagation was perpendicular to each other, and we used to call it as transverse electromagnetic wave, right? Also what we used to call it, uniform plane wave. Uniform plane wave. So this we have already studied in our wave propagation chapter, but there was no boundaries. Our wave was traveling in open space, right? This we have already studied. What was the name of this particular topic? The name was normal incidence, right? Normal incidence. We studied about normal incidence as well. We studied about oblique incidence as well. So let's revisit our normal incidence. So what was happening? A wave was traveling like this, and then there was a conducting surface. Now I am taking conducting surface. It could be any kind of dielectric. Here could be some M1 medium, here could be M2 medium, but I am taking this as a conducting plate. So this is our conducting plate. Our conducting plate is like this. So this was our conducting plate, and our wave was propagating like this. This is how our wave was propagating. Electric field was dancing in this direction, and the magnetic field was dancing in this direction. Let's just give the name of the directions. So if I am calling this as x, this as y, and this would be my z. So electric field was dancing in x, magnetic field was dancing in y, and x cross y direction of propagation was in z. Then what will happen? It will strike on the conducting plate. Since the conducting plate has neta equals to 0, so what will be the reflection coefficient? Reflection coefficient will be neta 2 minus neta 1 upon neta 2 plus neta 1. If neta 2 is 0, then reflection coefficient will be minus 1. So complete wave will be reflected back. Complete wave will be reflected back. Now what will happen is that electric field will change its direction. Electric field will change its direction, but the magnetic field will dance in the same direction. So this was your reflected magnetic field and reflected electric field, and this was your incident propagation. This was your reflected propagation. Now here what you will get, incident wave is there, reflected wave is there. Both superimposing, what they will make? They will make a standing wave pattern. So if I am calling this region as z less than 0 and this region at z greater than 0, so for z less than 0 I will get a standing wave pattern. And how will that standing wave pattern look like? Can you let me know? So you will have the standing wave patterns for electric field as well and magnetic field as well. But since your gamma E is minus 1, it is negative. That means here you will get maxima. That means at z equals to 0 you will get, not maxima, at z equals to 0 you will get minima. What is your gamma E? Gamma E is minus 1. If it is negative, then you will get minima, or you can check as well that how will you write down your total electric field in phasor form. So how will you write it down? Incident E naught e to the power minus j beta z. What about the reflected one? Reflected one will be minus E naught e to the power plus j beta z. Beta would be same because the medium is same, right? Now what we used to do? We used to take E naught e to the power minus j beta z as common. Then 1 minus e to the power 2j beta z would be left here. Now what will be the maximum value and minimum value? Maximum value will be 2 and minimum value will be 0. And now directly you can see at z equals to 0 you will get minima. Here you can directly see that at z equals to 0 you will get minima, right? After that maxima, minima, maxima, minima. So this is how your wave would go, right? Maxima, minima, maxima and minima. So at the conducting plate, if wave is coming at the conducting plate, at the boundary of the conducting plate, you get electrical minima. I should not say electrical minima, electric minima. What I should say, electric minima you get at the boundary of the conducting plate. And if electric minima is there, that means certainly magnetic maxima is there, because electric minima is equals to magnetic maxima, right? So this was your ETS that we have drawn, right? So this would have been your lambda by 4 distance, which is not useful, but we got to know that at the boundary of the conducting plate you will always get minima, then maxima, minima, maxima. This is for your electric field. And if you talk about magnetic field, then initially you will get maxima. If you talk about magnetic field, initially you will get maxima, then minima. Although magnetic field component will be lesser, so I should have made it like this: maxima, minima, maxima, minima, maxima, minima, in that manner. So by the yellow pen I am showing your magnetic field component. So if electric minima is there, that means magnetic maxima is there. So this we have already studied. All these will be used in our waveguide. That's why we are revising it. Okay. Now one more thing we have studied. If there is a conductor and we give it a charge, so where that charge will be stored? The charge will be stored on the surface. Also, the electric field will always be perpendicular to the surface, right? Electric field will always be perpendicular to the surface. So this component will be non-zero. The tangential component will always be 0 only. So this tangential component will be equals to 0. So electric field will always be normal. Like from here as well, it will be always normal. So all these will always be normal, right? Okay. So this we have seen. Now one last thing. So if ES expression is given and I ask you to find propagation vector, then you know how to do it. What we do, it E naught e to the power minus j something. So that something we used to call as phi. Then what we used to do, we used to take the gradient, and that gradient was known as propagation vector. And what was the direction of propagation? Direction of propagation was the direction of this vector. And what is the direction of this vector? The direction of this vector is equals to AZ cap. Direction of this vector is equals to AZ cap. So this was the direction of propagation. This was the direction of propagation, and this was your propagation vector. Same for this. Here what would be your propagation vector? 0.866 AX cap plus 0.5 AY cap. And what would be the direction? The unit vector in this direction. What will be the unit vector? If you know, the magnitude of this square plus this square will be 1 only. So what will be the direction of propagation? Direction of propagation is this, right? Now you let me know one thing. Here if I see my k vector, that is 0.5 AZ cap. So here my wave is propagating in z direction. My wave is propagating in positive z direction. That means I am only having kz component now. Let's just say I call k as kx ax cap plus ky ay cap plus kz az cap. So if wave is propagating in z direction, then I am only having kz component, right? If wave is propagating in x and y direction, then I am having kx and ky component. Is that easy for you, right? We will make some conclusion out of it. When we study waveguide, we will make some conclusion out of it. That's why we are revising all these things. So that's the only thing which you need to revise from your EM wave. So even if you haven't studied EM wave, still now you will get a basic idea of waveguide. So these were the things that you need to revise. So this we have revised. So what was the last slide? In last slide we calculated the propagation vector, also the direction of propagation. Okay, and we got to know that if my wave is propagating in x and y direction, then I am having kx ky. If wave was propagating in z direction, then I am only having kz. Now we study about waveguide. So what is a waveguide? Have you seen this matchbox? So you can assume this as a waveguide. Okay, upper side you are having some surface, downward you are having some surface, here you are having some surface, here you are having some surface, but this side is open. Like from here my pen can pass through. These sides are open. Which side? These sides are open. So in the similar manner, you have put this matchbox on XYZ plane, or you can say on XYZ coordinate. So these sides are these sides are not open, these are closed. This side is closed, this side is closed. Okay, the other side here is also closed. The other side that is here, which is not visible, that is also closed. The downward side is also closed. Which is not closed? This is not closed, right? Which is not closed? This is not closed. Here the entry is not closed, and from here it can come outward, that is not closed. So this side, which is open, this is open, and from backward also this is also open. So two sides are open. Now previously in our first chapter or in our second chapter, our wave was traveling in open space. The space could be anything, but now it will travel into this box. Now this box is made of perfect conductor. So this surface, this surface, this surface, this surface, all these surfaces are perfect conductor. That means your sigma is equals to infinity. Okay, and inside, as of now, what is there inside? Inside there is air, but there could be any dielectric, any kind of dielectric medium could be there. As of now, inside there is air, but there could be any kind of dielectric. But that dielectric is perfect dielectric. What do you mean by perfect dielectric? In the first lecture only we saw it. Perfect dielectric means sigma is equals to 0 and volume charge density is equals to 0. Okay. Now what will happen? Now in this box, in this empty space, wave will come. So wave is coming. Now like EM wave is coming. Now EM wave has three directions to go. It can travel in Y direction, it can travel in X direction, it can travel in Z direction. Let's just say the wave started traveling in Y direction first. Okay, it can travel into all three directions, X direction as well, Y direction as well, and Z direction as well. The wave is coming, it can travel in all three directions. Now we are assuming that first wave is traveling in Y direction. So if it travels in Y direction, what will happen? It will travel like this. This is the Y direction. So just as it goes upward, what it will see? A conducting surface, right? On the upper side, there is a conducting surface available. If I call this as x equals to 0, okay, and this as x equals to a, this coordinate is x equals to a, this is your y equals to 0 as well, and this I am calling as y equals to b as well. So what is the equation of this surface, upper surface? Y equals to b, right? The equation of this upper surface is y equals to b. So the wave started traveling in this manner. So here it will strike this surface. It will strike this y equals to b surface. And just as it strikes that surface, what will happen? It will be reflected back completely, because your gamma e would be -1. And these two combined, what they will make? They will make the standing wave pattern. And what kind of standing wave pattern you will get? That at the boundary you are having minima, then maxima, then again minima, then maxima. In that manner you will get. Now how many maxima you will get, how many minimas you will get, that will depend on this length b. Are you able to understand what did I just say? That my wave will propagate, it can travel in x, y, z in all three directions. First it tried traveling in y direction. What happened? It made a standing wave pattern, because there was a conducting surface, upper side it strike and then reflected back, and both incident and reflected back wave made the standing wave pattern, right? Because we have already seen this, that incident and reflected will make the standing wave pattern. Here I have only drawn the electric field. What I am drawing this only I am drawing the electric field in y, not in y direction, because this is the direction of propagation. So just I am saying that this is electric field I am drawing. Okay, this electric field I am drawing. Now in all three directions it can propagate. So in y direction it is making standing wave pattern. In x direction what it will make? Let's just say it travels in x direction. It travels here. So let's take this surface. What will be the equation of this surface? This surface. What will be the equation of this surface? X equals to a. The equation of this surface will be x equals to a. Let me take a break. Yeah, so this is our x equals to a surface. So in between I need to take some breaks, because my health is not that again good. I am having cough. So in between I need to take breaks. So please cooperate with that. Okay. Yeah. So there is x equals to a plane. X equals to a plane is there. So now wave will come. Wave will come. Now it will strike on this x equals to a plane. It will strike on this x equals to a plane. What will happen? It will be again reflected back, and incident and reflected back, both wave combined, what they will make? They will make the standing wave pattern. Are you getting this point? they will make the standing wave pattern. And here you will get minima, then maxima, then minima, maxima, minima. How many maxima and minima you will get, that depends on this length E. Are you getting this point? What is happening in x and y direction? In y direction it came, it saw the conductor, reflected back, incident and reflected back, made the standing wave pattern. Same goes for x direction. It came, saw the conductor, incident and reflected back, combined will make the standing wave pattern. At the boundary you will get minima, then you will get maxima, but and the certain same goes for your y equals to b plane as well. And what if the wave was traveling like this? If wave was traveling like this, that it will strike y equals to 0 plane. It can strike y equals to 0 plane as well, no? This is your y equals to b plane. What is this plane? Y equals to 0 plane. So it can strike y equals to 0 plane as well. So if it is striking y equals to 0 plane, then the same thing will happen. Incident and then reflected back. What if the wave was traveling like this? That it can strike x equals to 0 plane as well. What is this plane? What is the equation of this plane? This is your yz plane. So the equation of this plane is x equals to 0 plane. So what if the wave was traveling like this? So again incident would be there and complete reflection would be there. Incident and reflected combined will make the standing wave pattern. So again the same thing will happen, and at the boundary you will get a minimum. So in any x direction or y direction, if the wave is traveling, what it is making? It is making the standing wave pattern. So in x and y direction, what you are getting? Standing wave. Standing wave in x and y direction. Standing wave in x and y direction. What about z direction? In z direction, is there any conducting plate? No, it is completely open. So in z direction, the wave can propagate, right? Because in z direction it is open, no? This side is open. So from here wave came, then it can travel. So in z direction, the wave can travel. So traveling wave, SW stands for standing wave, okay? Standing wave. So you get traveling wave in a z direction. It could be in any direction, but we will take positive z direction, okay? So what happened here was, you incident a wave in the waveguide. A wave is going. If it goes in x direction, it will make standing wave pattern. If it goes in y direction, then it will again it makes a standing wave. But in z direction, it can propagate. So in x and y direction, you will get standing wave, and these standing waves will propagate in z direction. This is what is happening in your waveguide. In open space, what was happening? The wave was traveling in z direction, then electric field was dancing in x and the magnetic field was dancing in y. Or what can happen, that electric field can dance in both x and y as well. This we have already seen. In the derivation, we saw that electric field can dance both in x and y as well. And then magnetic field will dance in y and minus x. So magnetic field can also dance in y, magnetic field can also dance in x and y. But both cannot dance in z direction, because this is the direction of propagation. Okay, this was the scene, that EH, and they were moving ahead. This was your EH, and they were moving ahead. We have seen the simulation as well. But here the visualization is very difficult. What is happening here? Electric field, magnetic field, electric field, magnetic field. Now this I have already shown at this particular surface. Now in the waveguide as well, this will be happening. No, like what I mean to say is that the same thing will be happening here as well. The same thing will be happening here as well. The same thing will be happening here as well. So in the complete waveguide, this thing will be happening. So this standing wave will be traveling in positive z direction. In x direction, you are having standing wave. In y direction, you are having standing wave. And this combination of standing wave is traveling in z direction. This is what is happening inside the waveguide. This is the core concept. Is that clear to you? Okay. Now you just let me know, smartly you will let me know that what will be your propagation vector. Wave is traveling in z direction. So will I write down my propagation vector as kz az cap? Because here what we saw, that if wave is propagating in z direction, then kz az cap. And if wave is propagating in x and y, then kx and ky would be coming. Here wave is propagating in z direction. So will I write down only kz cap? No. Why is that so? Because what does this propagation vector shows? The propagation vector shows that there is a wave in z direction. There is a wave in x and y direction. So let me know one thing. Is there any wave in x direction? Yes, certainly there is a wave, no? Unfortunately, that wave did not become a traveling wave. That wave became a standing wave. but certainly there is a wave in x direction. And if there is a wave, then it will have its beta. And if there is a beta, that means kx will come in action. What is kx? Kx is actually beta only, no? If I take the under root of kx square plus ky square, what that would be? Beta only. So if the wave is having any component in x direction, then certainly it will have its own beta. If beta is there, that means kx is there. If the wave is traveling in, it is not traveling in x direction. It tried to travel, but eventually it became standing wave. It tried to travel in y direction, but eventually it became standing wave. But certainly wave once traveled, right? Certainly there is a wave. In x direction also there is a wave, in y direction also there is a wave, in z direction also there is a wave. In x and y direction, the wave is standing wave, and in z direction, the wave is traveling wave. So certainly the waves are there in x, y and z in all three directions. So if the wave are there in all three directions, then certainly they will have the kx cap as well, kx ax cap as well, ky ay cap as well, and kz az cap as well. Okay, are you getting this point? In x direction, in y direction, in z direction, all three direction wave is there. In x and y direction, standing wave is there, and in z direction, traveling wave is there. So our wave is propagating in z direction, making the standing wave pattern in x and y. So what do you think? What you will call as kx? Kx is your propagation constant or wave constant, whatever you want to call. Propagation constant in x direction, propagation constant in x direction. Now same goes for ky, propagation constant in y direction. They are known as selective propagation constant as well, like different name you can find in different textbook. Okay, and this is propagation constant in z direction. Well and good. Okay, let's see a simple question. Now let me know where you will get standing wave, where your wave will propagate. If this is your waveguide, then in which direction your wave will propagate and where you will get your standing wave. This I am calling as x. This is your y equals to 0. Okay, z is equals to also 0. This I am calling as z equals to b, y equals to a. So in which direction you will have standing waves and in which direction the wave will travel. So you can directly see that conducting surface are there at z equals to 0 and z equals to b, at y equals to 0 and y equals to a. So in y and z direction you will have the standing waves and the wave will travel in x direction. So traveling wave in x direction. From here you can tell it is positive x, right? It is positive x only, because if this is x equals to 0, so wave can travel in this direction only, no? Wave can travel in this direction only. So that will be positive x only. So here I can say that the wave, traveling wave is in positive x direction, and and standing waves are there. Standing waves will be there in y and z direction. Well and good. Okay, let's see the derivation now. We will see the wave equations. Wave equation inside the waveguide. So inside the waveguide, what do we name? This as x equals to 0 and y equals to 0 as well. This point is x equals to a. This is your a. So this surface is known as, the equation of this surface is x equals to a, and this point is b. So basically this width is a, or you can call it length, and this length you can call as b. Usually what do we do is that a is greater than b. Always remember this thing, that a is greater than b. Okay, this is what we take. So in x direction we take the longer length, in y direction we take the smaller length. A, b. A is greater than b. This is your x equals to a. This is your, what is this plane? This plane is y equals to b. Certainly this plane is your x equals to 0, and the downward plane, this lower plane is your y equals to 0. Now in your EM wave propagation in open space, like there was this open space, there was no conducting surface, there was no waveguide. If the EM wave was propagating in open space, then at that time your EZS would have been 0, because the wave is propagating in z direction. Here I can write down wave propagation in z direction. Wave propagation in positive z direction, and standing waves in x and y direction. So if wave is traveling in z direction, then EZS would have been 0 if it was traveling in open space, but now it is traveling in waveguide. So EZS is not equals to 0. Neither your EXX would be 0, neither EYS would be 0, neither EZS would be 0. Neither your HXX would be 0, HYS, HZS would be 0. So none of them will be 0. What I mean to say is that if the wave is traveling in positive z direction, then it can dance, the electric field can dance in z direction as well. If the wave is traveling in z direction, then electric field can certainly dance in x direction, it can certainly dance in y direction, but when it was traveling in open space, it could not dance in z direction. But now it can dance in z direction if it is traveling into a waveguide. Is that clear to you? In the end of this chapter, we will see the field visualization as well. Then it would be more clear to you. But as of now, you can remember it that inside a waveguide, the electric field can dance in any direction. It doesn't matter what is your direction of wave propagation. But in this is known as rectangular waveguide. Why this is known as rectangular waveguide? Because this is rectangular, no? So this is known as rectangular waveguide. So in rectangular waveguide, in the next lecture, we will study about the modes. So there will be transverse electric mode and transverse magnetic mode. So based on that, we will decide the value of EZS and HZS. But as of now, what you will remember that electric field can dance in any direction and magnetic field can dance in any direction. If the wave is traveling in positive Z, then electric field can dance in X, it can dance in Y as well, it can dance in Z as well. Everywhere it can dance. Is that clear to you? So this is known as our rectangular waveguide. We need to study about two waveguides. The first one is rectangular. So it is like a cuboid, right? This is like a cuboid, but not perfect cuboid because these surfaces are open. These surfaces are open, but in case of cuboid, these surfaces would be closed. Then we need to study circular waveguide. What do you think? What kind of structure would be there? Cylindrical, right? From here wave will propagate. So that we will study later on. But as of now, we are studying rectangular waveguide. So what we have seen, this was our waveguide. X and Y direction will have the standing wave. In Z direction, we are propagating. The direction of wave propagation is Z, but still it can have any component. It can dance in X direction, it can dance in Y direction, and it can dance in Z direction. Same goes for magnetic field. Is that clear to you? Now we will derive all these expressions Ex, Ey, Ez, Hx, Hy, Hz using Maxwell's equation. But that derivation is not important at all. Okay, you will use this vector Helmholtz equation, and certainly your rho is equals to 0 and sigma is equals to 0 and rho is equals to 0. And here in place of gamma, I am gonna write gamma g. What is the difference between gamma and gamma g? Gamma is the propagation constant for open space. Propagation constant for open space. Or you can say propagation constant for uniform plane wave. What I mean to say is that if the wave was propagating in open space, like there was no conductor, then what would have been the gamma? This would have been the gamma. And what do you mean by gamma g? Gamma g means guided propagation constant. Guided propagation constant inside the waveguide. That means if the wave is propagating inside the waveguide, then what would be your propagation constant? So that would be gamma g, and that is known as guided propagation constant. So we will find all the parameter inside the waveguide and inside the waveguide and outside the waveguide, you can say, or for uniform plane wave. So these parameters we have already found, right? Gamma, alpha plus iota beta. What is the value of alpha? What is the value of beta for different mediums? We have found out. We will be finding out gamma g as well. So that we will see in next lecture. But as of now, you will write gamma g here. What do you mean by gamma g? Gamma g is the propagation constant inside the waveguide, and gamma is the propagation constant outside the waveguide. That means if the wave was uniform plane wave, if the wave was propagating in open space, then what would have been your gamma? What would have been your propagation constant? That would have been your gamma. Okay. So when you solve these equations, you will get the expression of EZS. Now, how did I get the expression of EZS? That mathematics no one will ask you, and nowhere it will be used. I can write it on paper. In any time, in any gate examination, from here to here, whatever the steps are involved, those are very complex mathematics as well, and those steps will never be asked. So you can directly write down your Ez as component, and the component that I am going to write down now, that also you do not need to mug up. Okay, so now I am going to write down the expression of Ez. So what that would be? That would be A1 cos kxx plus A2 sin kxx plus A3 cos kyy plus A4 sin kyy e to the power minus j gamma g z. Wave is propagating in positive z direction, right? Wave propagation is in positive z direction. So certainly e to the power minus j gamma g z would be coming. That is for sure. You have no doubt about this. E to the power minus g gamma j z. Really sorry. This j wouldn't come, no? Really sorry, this j wouldn't come. So e to the power minus gamma g z would come, because gamma g could be equals to j beta. There j would come. So if wave is propagating in positive z direction, if our wave was propagating in positive z direction, then what was our E field equation? That was E naught e to the power minus j beta z, and j beta could be replaced, if it is having reflection coefficient, then j beta would be gamma. So E naught e to the power minus gamma z. That means wave is propagating in positive z direction. So certainly wave is propagating in positive z direction. That's why e to the power minus gamma g z would be there. There is no doubt about that, right? Now what about these components? So in x and in y, both sinusoid and cosinusoid components you are having. Both sinusoid and cosinusoid components you are having. What does this represent? This represent standing wave patterns. That in x and y you are having standing wave pattern, and our field is propagating in z direction. Now we will simplify this expression, okay? This is not the final expression. This is a generalized expression. We will simplify this expression using boundary condition, and those boundary conditions are important. From there questions can be framed. But how did you reach to this conclusion? That is not important. And also you do not need to mug up this particular expression. So what these are? Standing waves. Standing wave in xy direction. And what is this? This is that traveling wave. Here you can have standing wave in x direction. So either you will have sinusoid component, or you will have cosinusoid component, or you will have sinusoid component. As of now we have written both of the components. I am not sure which component I will have, either sinusoid or cosinusoid. In y direction you will have standing wave. You can either have sinusoid component or cosinusoid component, but I am not sure which component I will have, so I have written both of the components. We will find out which component you will have, so that we will find out later on. But are you getting this point? In x direction you are having standing wave, in y direction you are having standing wave, and wave is traveling in z direction. So this is how it is represented. The same thing can be written for hzs as well. How will you write down? That in x direction it will have standing wave, in y direction it will have standing wave, and then the direction of propagation would be there. So just this constant will be changed. Here I am writing A1, so here I am writing B1. In x direction it is having standing wave. It could have sinusoid component or cosinusoid component. In y direction as well it will have standing wave. It could have sinusoid component or sinusoid component. And in the end, intuitively also I will tell you that why it is having sine or cos. Like one of the component will be there. Here A1 would go to 0 and A3 would go to 0. So that we will prove using boundary condition. Then with the intuition as well, I will tell you that why A1 and A3 went to 0. But you need to have the patience, okay? E to the power minus g gamma z. So same goes here. This was your traveling wave, this was your standing wave, and this was your standing wave. So this expression you do not need to mug up. Just you need to think that, just you need to know that if the wave is traveling into waveguide, then it can have EZS, EXS, EYS, or HZS, HXS, and HYS. All the components it can have. We have written down the equation of EZS and HZS. What it is showing? Standing wave in X, standing wave in Y, both can have sinusoid or cosinusoid component, and the wave is traveling in positive z direction, e to the power minus gamma g z. Same goes for magnetic field. Now we need to find out the expression of EXS, EYS, HXS, and HYS, and those will be derived using Maxwell's equation only. But how those expressions are derived, that is of no use, absolutely no use. So eventually you need to remember the expressions, and now I will tell you how to remember those expressions. So now using EZS and HZS, we need to find EXS, EYS, HXS and HYS, because our electric field is, what is our electric field? It can dance in X, it can dance in Y, it can dance in Z. Same goes for magnetic field, it can dance in X, it can dance in Y, it can dance in Z. So Z expression we have find out, from here we got the Z expression, but how did we get it? No use. Now using these two guys, we will find these guys. And how we will get it? No use, but what is the final result? That is useful. So we will write down EXS, EYS, HXS and HYS. So in all the expressions, first minus gamma G upon H square would come. So whenever you need to write down EXX, EYS, HXX and HYS, you will always write down minus gamma G upon H square. Now you will feel that, sir, how we will remember this? So in a longer run, you would be able to remember, because we are going to use these equations again and again. Again and again we are going to use it. So in a longer run, certainly you will be able to remember, and you should remember it. Okay. Now here X is there, here X is there, so I will write down del y del X. Here Y is there, so I will write down del y del Y. Here X is there, so I will write down del y del X. Here Y is there, del y del Y. Okay. Now here electric field is there, no? So what I already know, I do not know EXX, I do not know EYS, I do not know HXX, I do not know HYS. What I already know EZS. Here E is there, so I will write down something of E only. EZS. Here E is there, so I will write down something of E only. Here H is there, so I will write down something of H only. Here H is there, I will write down something of H only. So first step is done. The expression is not complete, but first step is done. What we did, minus gamma G upon X square. Then here X is there, del y del X. Here Y is there, del y del Y. Here X is there, del y del X. Here Y is there, del y del Y. Here E is there, so EZS. E is there, EZS. H is there, HZS. H is there, HZS. Now I will tell you two lines, you need to remember it for complete waveguide. Okay. What are the two lines? Two lines are, Isha is sweet. Okay. And Himanshu is careless. So these two lines you need to keep in mind. Isha is sweet and Himanshu is careless. Himanshu is your educator, he is careless because he is delaying it and he is always sick. उसकी तबीयत कभी ठीक नहीं रहती, so he is careless. I am careless, I know. And Isha is sweet. Isha is any random name, I do not know her. Okay, do not make any assumptions. So Isha is sweet. So these two will help a lot. Okay, these two lines will help a lot in remembering the formulas. Now here some term would come. What that term would be? J omega mu upon H square. Here also some term would come. J omega mu upon H square. Here the term would be J omega epsilon upon H square, and here the term would be J omega epsilon upon H square. But here plus minus sign you need to find. Now Isha is a sweet girl and she broke up with someone. So Isha's X will be positive or negative? Isha broke up with someone. She was a sweet girl. Now that guy who broke up, he will be positive or negative? She lost a sweet girl, no? So that guy will be negative. Are you getting this point? Look, in a sign there would be very confusion. So this is the best thing. Isha is a sweet girl. So Isha's X would be negative. And Himanshu is careless. So Himanshu's X will be positive because she lost a careless guy. So Himanshu's X will be positive, but Isha's X would be negative because Isha's X lost a very sweet girl. So that guy would be negative, but Himanshu's X lost a careless guy. So that girl would be positive, right? So this is the way to remember. EX, Isha's X would be negative and Himanshu's X would be positive because Isha is sweet and Himanshu is careless. And these expressions will be used later on as well. These two lines will be used later on as well to remember the formula. In longer run, you would be able to remember the sign. But in a shorter term, in shorter memory, if you need to remember it, then this is how you can remember it. Secondly, if this is minus, then next expression would be plus, and if this is plus, next expression would be minus. So this is how you can keep in mind. That HX expression I remember, EX expression I remember. HX, Himanshu's X, Isha's X. Those expression I remember. Isha is sweet, so his X would be negative. Himanshu is careless, so her X would be positive. So positive sign. Here what will come? So here del by del. Here X is there, no? So opposite Y would come. Here Y is there, no? so opposite x would come. Here x is there, no, so opposite y would come, and here y is there, so opposite x would come. Here E is there, so here opposite HZ would come. Here E is there, so basically whatever here is there, just the complete opposite is coming here. Whatever you are getting here, the complete opposite is coming here. Y x E h, x y h e, y x h e, right? Now there would be confusion in this mu and epsilon, like they will be interchanging mu and epsilon. Sometimes while writing down the formulas, what students think is that they interchange these mu and epsilon because it is tough to remember. So how will you remember? B equals to mu h and D equals to epsilon e. This you remember, no? So mu always comes with h and epsilon always comes with e. So if I am writing mu, the next would be h, and here you will remember that h would come. Why is that so? Because this step you would have already written. So if this step you would have already written, then you can write down this step very easily. And you see that if hz is there, then certainly mu will come here. That's it. And if e is there, then epsilon would come here. So e always come with epsilon and h always come with mu. So that confusion is also gone. So will you be able to write down these expressions very easily? Any expression if I ask you to write, let's just say randomly at a random day, at a random hour, I ask you to write down the hxs expression. So how will you write down hxs expression? Okay, hxs expression I am asking you to write down. What you will think that, sir, first step is minus gamma g upon h square. Then sir, del by del x. Then sir, h is there. So what do I know? I only know hzs. Now sir, here sir, if z is there, then e would come. Here del by del y, ezs would come. That I am pretty sure. So if ez is coming, that means j omega epsilon would be coming, because epsilon always comes with e, divided by h square. Now what about the sign, sir? Himanshu is a careless guy. Her x would be positive. There you go. If you practice it enough 2 or 3 times, it is very tough for the students to remember these formulas. They just mug it up. But this is the best way to remember it. Let me tell you guys, this is the best way. And just remember these 2 things. These will be used later on as well. In the next lecture as well, these will be used. Okay. So these will be used. And if someone is having the name Isha, don't get offended. I don't know why would you get offended. I am calling you sweet only. I am calling myself careless. And if someone is having Himanshu name, then don't get offended. Okay. I am calling myself careless, not you. So that's the way to remember. Now, on a random day at random hour, I ask you to write down the expression of EYS. What you will say that, sir? Minus gamma g upon h square. What is this h square? This is new. So I did not discuss about it. H square I will discuss about it. Okay. So minus gamma g upon h square. Sir, here y is there. So del by del y. What do I know? If e is there, so ezs. So next, complete opposite would come. If h is coming, j omega mu would come, divided by h square. So ex expression I remember. Isha is a sweet girl, so her x would be negative. So this would be positive. In the previous way, you are having negative, then here you are having positive. Here you have positive, then here you are having negative. That's it. So this is the way you have written it down. Okay. So this is how you will be writing it down. Now in this expression, will you ask me what is kx? Will you ask me what is ky? No, you will not ask me, because I have already told that what is your kx and what is your ky. Here I have already told. Propagation constant in h direction, propagation constant in y direction. Now what is this h square? H square. So I will write it down. This is very important. Okay, very, very important. This is very important. So h square is equals to kx square plus ky square, and that is equals to gamma g square plus omega square mu epsilon. Now you know about everything, right? You know kx, you know ky, you know gamma g, you know omega mu epsilon for sure. Omega is the frequency of our EM wave, mu epsilon you already know. Gamma g is the guided propagation constant, kx is the propagation constant in x direction, propagation constant in y direction. Now what is h called as? What is your h actually? Kx square plus ky square, right? H is kx square plus ky square. Then what do you think how this under root kx square plus ky square would have come? from this thing, right? Where our wave is propagating? Our wave is propagating in z direction. So x and y are transfers to the wave, right? X and y are transfers to the wave propagation direction, because wave is propagating in z direction. So x and y are transfers. And what is kx and ky? Propagation constant. So h is known as transverse propagation constant. How did I define h? That h is under root kx square plus ky square. And how it would have came? From kx ax cap plus ky ay cap. Wave is propagating in z direction. So x and y would have been transferred. So x and y would have been transferred. Now what is kx and ky? Kx and ky are your propagation constant in x direction and y direction respectively. And if you combine both of them, then what you will write down? Transverse propagation constant. Why transverse propagation constant? Because direction of propagation is z. So in x direction and y direction, those will be transverse to that. I hope you remember, we used to call transverse electromagnetic wave, because E, H and direction of propagation was perpendicular to each other. So similarly, H is known as transverse propagation constant. Okay. No one will ask you this. No one will ask you. But if someone is having curiosity that what is the meaning of H, then this is the meaning of H. The H is the transverse propagation constant. And that is equals to kx square plus ky square. And this is very important. That is equals to gamma g square plus omega square mu epsilon. Is that clear to you? So till now in this lecture, what we have studied? We have studied that first we studied EM wave in open space. Now if wave travels, I will give the complete summary now. This is the complete summary, whatever that we have studied in this complete lecture. So if the wave is getting into a waveguide and the waveguide is put such that it can travel in z direction, that there are no boundaries in z direction, but there are boundary in x equals to 0 and x equals to a, y equals to 0 and y equals to b. So boundaries are there at x equals to 0, x equals to a, y equals to 0 and y equals to b. So there are conducting plates. Now if the wave comes, it will strike x equals to a, then make the standing wave. It will strike y equals to b, will make the standing wave. So in x and y direction you will get the standing wave, but in z direction there are no conducting plates, so it can propagate. So our wave will propagate in a manner that in x and y direction it will make standing wave and it will propagate in z direction. Now our electric field and magnetic field both can have Ez as component as well and Hz as component as well. No matter, even if the wave is propagating in z direction, the electric field and magnetic field both can dance in z direction as well, x direction as well and y direction as well. For z direction, in x and y we get the standing waves. So we will get the sinusoid component and cosinusoid component both in x direction, and the same goes for y direction as well. But one of them will be true, like one of them will be going to 0. This will be going to 0 and here this will be going to 0. And why this will be going to 0? What does it represent? That we are going to see in the next lecture, right? Along with that, using the EZS and HZS expression, how we can find EXS, EYS, HYS and HXS. So that trick we have already seen. Minus gamma g upon x square, del by del x, del by del y, del by del x, del by del y, then EZ, HZ, HZ, then j omega mu, j omega mu, j omega epsilon, j omega epsilon. Two line we understood that Isha is sweet and Himanshu is careless. So Isha's x would be negative after breaking up and Himanshu's x would be positive. And rest would be negative, positive, positive, negative. There you go. So this is the conclusion of our complete lecture. Till now we have studied the basics of a rectangular waveguide. Is that clear to you? Now we will see the modes of propagation. What we are going to see? Mode of propagation. That our plane wave, uniform plane wave was propagating in transverse electromagnetic wave. That this was the direction of propagation. E and H was perpendicular to each other. So that was our TEM mode. Now in waveguide, there would be TEM mode, there would be TM mode, there would be TE mode. So that mode we are going to study in next lecture. So very in-depth, in a very in-depth manner we are going to discuss that. So next lecture will be bigger. It would be roughly around 2.5 hours. But this was a small lecture only of 50 minutes. Okay, so I hope you enjoyed it. So this was our introduction to waveguide. In the next lecture, we will study about the modes. Thank you very much.